The topic of this video is what the formal definition of a limit is, or in other words, what the epsilon delta definition of a limit is, and how to apply this definition to prove a limit. So what is the formal definition of a limit? Let's start with something we know. So we're going to solve a really simple limit problem first, and what this problem says is the limit as x approaches 1 of x squared minus 1 over x minus 1 is basically 0 over 0, or the indeterminate form. So instead we're going to pick some x values that approach 1 and see what f of x tends toward. So we're going to pick 0.5, 0.9, 0.99, 0.999, and so on. And from the table of values, we can see that f of x approaches 2. So we can conclude that as x approaches 1, f of x approaches 2, or the limit of f of x is just 2. Let's do another simple limit problem before I start to explain what the epsilon delta limit definition is. So this time we're looking at a graph, and we can tell that the limit as x approaches a is L. So we can write the statement, the limit as x approaches a of f of x is L. We can then use this prior knowledge to base the epsilon delta limit definition on. So now what is the epsilon delta limit definition? If we look at the graph below, we can apply the epsilon and delta concepts. The essence of the epsilon delta limit definition is basically, if you give me the epsilon value, or the range of the y values, so epsilon is basically the range of the y values, and here is L plus epsilon, and here is L minus epsilon, and the distance is basically epsilon. I can give you the delta, or the x value ranges, and here is a plus delta, and here is a minus delta, and again the distance for both is delta, where if you choose a x value in this range right here, I can guarantee you a f of x value in the range between L minus epsilon and L plus epsilon. To explain it algebraically, let me first write the actual and formal statement of the epsilon delta limit definition. So the absolute value of x minus a is greater than 0 but less than delta. And if you choose a x value in the range as noted in this statement or expression basically guarantees us a f of x value in the range of the absolute value of f of x minus L is less than epsilon. To explain this a bit more clearly, we can first enlarge the x-axis and the y-axis a little bit. So here on the x-axis, this is a plus delta, this is a minus delta, and the distances here are delta. So what the expression is saying is that I can choose a x value where the distance from a is not 0, so the value of a can't be a itself, but the distance between x and a cannot be delta either. So the value of x cannot be a plus delta, nor can it be a minus delta. But the value of x can be anywhere between a minus delta and a plus delta. If we do follow this guideline, we can be guaranteed a f of x value in. So now let's blow up the y-axis. Here's L. Here's L plus epsilon, and here is L minus epsilon. And the distances here are epsilon. Now what the second part of the expression is saying is that the distance between f of x and L is less than epsilon, so we can be guaranteed a f of x value in the range between L minus epsilon and L plus epsilon. So no matter how small the epsilon or delta value may be, or no matter how small the range you give me may be, as x gets closer to a, so as the delta value gets smaller, f of x will get closer to L, so the range value will get smaller, and vice versa. So that's basically the essence of the formal definition of a limit, or the essence of the epsilon delta limit definition. So now we're going to apply this definition to prove a limit. To use this definition in a proof, we want to go from 0 is less than the absolute value of x minus a, which is less than delta, to the absolute value of f of x minus L is less than epsilon. And in order to do this, we need to find a formula for delta in terms of E, or need to find a formula for epsilon in terms of delta. And that's basically manipulating the expressions or guess and check. So looking at this first example problem, we have to prove that the limit as x approaches 3 of 2x plus 4 is 10, using the formal definition of a limit. So we can assign values to these numbers mentioned. Because x approaches 3, 3 is a. 2x plus 4 is f of x, and 10 is L. The first step is to play around with the expressions a little bit to find a formula that ties the from expression to the to expression. So we're going to start with the absolute value of f of x minus L, which is less than epsilon. And now we're going to plug in the values that we know. So the absolute value of 2x plus 4 minus 10 is less than epsilon, because f of x is 2x plus 4 and L is 10. So now we're going to factor out the 2 and bring the 2 to the other side to simplify the expression. And we end up with x, the absolute value of x minus 3 is less than epsilon divided by 2. And we can see from this expression that it resembles the from expression, except for the fact that delta is epsilon divided by 2. So that's basically our formula that ties these two expressions together. Delta equals epsilon divided by 2. So step 2 is to test the formula. So now we're going to start with the expression 0 is less than the absolute value of x minus a, which is less than delta. And we're going to plug in 3 for a and epsilon divided by 2 for delta, which we found in step 1. So now we're going to manipulate the expression and simplify it. And we end up with 0 is less than the absolute value of 2x minus 6, which is less than epsilon. So now we're going to expand negative 6 into plus 4 minus 10. So we result in the expression 0 is less than the absolute value of 2x plus 4 minus 10, which is less than epsilon. And we see that this expression resembles the absolute value of f of x minus L, which is less than epsilon. So therefore, we have gone from 0 is less than the absolute value of x minus 3, which is less than epsilon, to the absolute value of 2x plus 4 minus 10 is less than epsilon, using the formula delta equals epsilon divided by 2. So we have proved that the limit as x approaches 3 of 2x plus 4 is 10.